use this truss to find the axial forces in the members using the method of joints. By definition of a truss, each of these joints is a smooth pin, which means that if the whole truss is in equilibrium, each joint must be in equilibrium. And we're going to take advantage of that in order to solve for the axial forces in these members using the method of joints. So the first step that we need to do is solve for the reactions at A and G. A is a pin, so we're going to have a reaction in the Y direction and in the A direction, or the X direction. At G, this is a roller, so we're only going to have a reaction in the Y direction. Since AX is the only force in the X direction, I can use the sum of the forces in the X direction is equal to 0 to determine that AX is 0. There are two forces in the Y direction, so I'm going to use the sum of the moments about A, which is equal to 0, to solve for the reaction at GY. So to do that, if I take the moments about A, I have a 4 kilonewton force times 2 meters, and a 5 kilonewton force times 4 meters, an 8 kilonewton force times 8 meters, 6 kilonewton force times 10 meters, and then GY times 12 meters. And if you solve for GY, you will get 12.67 kilonewtons pointing up. And then I can use the sum of the forces in the Y direction is equal to 0 to solve for AY. So that will be AY minus 4 minus 5 minus 8 minus 6 plus 12.67, which is the GY. And if you solve for that, AY is 10.33 kilonewtons in the positive direction. Now, we can pick any one of these joints to solve for, but let's say we wanted to solve for the axial force in AL and AB, then we would choose the joint A to solve for the axial force in each of these members. So again, if the entire truss is in equilibrium, then this joint A must be in equilibrium. So I can rewrite this joint A, just that little joint, and then all of the forces on that joint. Well, AX is 0, so I can ignore that. We have AY, which is 10.33. And then we have the axial force AL and AB. And I don't know which direction these are. I'm going to draw them both in tension. So I have AL and AB. And those are the three forces at joint A. When you're using the method of joints, you want to find a joint and start with one that only has at most two unknowns. The reason for that is all of the forces are concurrent through the joint, so you only have two equations of equilibrium. You have the sum of the forces in the Y direction is equal to 0, and the sum of the forces in the X direction is equal to 0. There are no moment equations when you are just solving for that joint. So I can start with the sum of the forces in the Y direction, and I have 10.33 up plus a portion of AL. And I happen to know that this angle here, if we look up here, this is a height of 3, this is a distance of 4, so this is a 3, 4, 5 triangle. So I can take the 10.33 plus AL times 3/5 is equal to 0. If I solve for that, I get AL is equal to negative 17.22. And this will be in kilonewtons. We got a negative force here. Of course, we can never have a negative force. What that is telling me is that I drew this in tension, and it really should be in compression. So I'm going to cross that out and draw it in the opposite direction. And I will write this as AL is equal to 17.22 kilonewtons in compression. And the reason that's important is because it's in compression here. If I move over to joint L, then it's also going to be in compression there. So this is going to be 17.22. So the negative and the positive sign don't really have any meaning. We need to use the compression or tension. But coming back here to this joint A, now I can use the sum of the forces in the x direction to solve for AB. So that will be AB minus AL, which is 17.22 times 4/5. And if you solve for that, AB turns out to be 13.77 kilonewtons. And since it is pulling away from the joint, we know that it is in tension. And so now I have just solved for the axial force in both AL and AB. I can then move on to, we can move on to joint L, for example. And we know we have the 17.2 coming from AL. Then I usually draw all of the forces in tension until I know what direction they are. So this would be LK, and then I have LB. And we could have done this to start with, but if you look at this, just by visual, without solving for anything, we know that LB is a zero force member because there are 3 forces concurrent at joint L. Joint L. 2 of them are collinear, so this one must be a zero force member. Okay, if we had a different loading, if there was some load applied at joint L, then this LB would carry a load, but right now it is not carrying any load, so it's a zero force member. And so by inspection here, I know that LK is going to be 17.22 kilonewtons, and it's going to need to be in compression so that these two will balance out. Similarly, I could move on to joint B here. So if I were to draw joint B, I would have the applied 4 kilonewtons. I would have AB, which I know AB is 3.77 kilonewtons in tension, so it's going to pull away. We know that LB is 0, so I don't need that one. And then we have BK and BC. So we have 2 unknowns and we have 2 equations to use. So I will use the sum of the forces in the x direction is equal to 0, and the sum of the forces in the y direction is equal to 0 to solve for BK and BC. So this one would be what? Negative 4 plus BK. And this angle now would be, let's see, we have 2, 3, and the square root of 13. So BK would be times 3 over the square root of 13. And so BK, if you solve that out, is 4.81 kilonewtons, and it is in tension. And then I can solve the sum of the forces in the x direction is equal to 0, and I have 4.81. This time it's going to be 2 over the square root of 13 plus BC minus 13.77. And so my BC is 11.1 kilonewtons in tension. So then once you have that, you could then move on to joint C, because now you have the B, and you could continue to solve the forces in each of these members.